Okay, here's part 2 of this run-through for this June 2024 Pearson Edexcel International A-Level paper, Unit 6, which is the practical skills in physics. So this exam will be on Monday for my students. This was last summer's paper from June 24. So I thought I'd do this as my last practice exam run through. So this also helps people preparing for linear advanced paper 3. Yeah, so linear advanced paper 3 will have a longer version of this Unit 6 paper the following week. So this is useful for both international A-level students and linear A-level students. In part 1 of this run-through, I went through questions 1, 3 and 4, and now I'm going to go through question 2, which looks at writing a method for a random experiment that you should be able to work out. The reason I didn't do question 2 in the first run-through was because I had scanned the document and one page hadn't come out properly. Okay, so here it is. And here's the question. All right. So it says a student investigated the flow of water through a horizontal pipe using the apparatus shown. Okay. Now I've just put a note here for myself. Check this. There are 2 methods to ensure the pipe is horizontal. Okay. So what have you got? You've got digital pressure gauges at each end of the pipe, and the flow of water is from the left to the right. Yeah, so this tube is connected to a tap, water tap, and the pipe has an internal diameter and is held up by 2 stands. Okay, now for it to be horizontal, you would expect this height to be equal to this height. Okay, so you could measure the height at both ends. Height 1, height 2, and if they're the same, you know it's horizontal. You could also use a spirit level to make sure the pipe is horizontal. You're then collecting the water in a beaker or some container, which is on a mass balance, which you should check for 0 error. So you can actually put your container on the mass balance and 0 it before the water comes in. And then it says the mass of water leaving the pipe in a given time is given by the formula where m is the subject of the equation, and it's got loads of different terms in it just to confuse you. Okay, pi you know. Rho is the density of the water in kilograms per meter cubed. P is the pressure difference between the ends of the pipe. And you can see you've got digital pressure gauges on the both ends. So the difference will be the difference between those 2 values. So delta P is measured by the 2 pressure gauges, and it will be in Newton per meter squared. Okay, then you need to work out R, which is to the power of 4, and R is the internal radius of the pipe. So you would probably use vernier, or better, digital calipers now that they have them, because it's accurate to 0.01 millimeter resolution. And of course that's SI units of meters. And then eta, so on the top, is T is for time, no doubt. Yes, the T is given as time. Yeah, above. Eta, Greek letter, is the viscosity of the water. Yeah, units we got to look below because they want us to work out the units as the only thing that we don't know. And L, the other unknown, so eta we done, P we done, rho we done, T we done. L is the distance between the 2 digital pressure gauges. So in other words, the pressure gradient would be delta P divided by L. That would be the pressure gradient. And that's what makes fluids flow, is a pressure gradient. Okay? So we got to show that, mathematically prove that the formula above gives the unit for eta as newtons seconds per meter squared. Okay? So obviously, if we want to change the subject of the equation, then the units of the left-hand side must equal the units of the right-hand side. So for any equation to be correct, the units of the left-hand side must be equal to the units of the right-hand side. Okay? That's what we're checking. So I've made eta the subject by putting m, dividing both sides by m, multiplying both sides by eta, and that means we can work out the units of the left-hand side, which should be eta, should be the units of the quantities that have units. Yeah, that means pi doesn't have a unit and the number doesn't have a unit, so we can eliminate those in terms of units. Density is kilograms per meter cubed, so that's rho. Pressure is newtons per square meter, so that's capital P. And R to the power of 4 will be meters to the power of 4. And T obviously is in seconds, so that's everything on the top. At the bottom we got mass, which is kilograms, and length, which is meters. All you've got to do is to simplify. Now you've seen that the kilograms will cancel out, and you want to put all the meter figures together. So you've got meters to the minus 1 divided by meters. So that's another minus 1, so it becomes meters to the minus 2. There's only one term with seconds in it, so second stays as S. And N I've left from pressure on its own. And there you go, the left-hand side is meters to the minus 2 seconds times newtons. So if you change that around, you can get it into the form that they've asked you to do. So we have shown that the units of the left-hand side, eta, is equal to newtons, seconds, meters to the minus 2. And there you have got your 2 marks. Quite a lot of work for 2 marks, but a very good skill to practice before Monday's exam. Being able to work out any unit is one of the skills of physicists. Part B, for question 2, the student used a meter ruler or meter rule to measure length between the 2 pressure gauges and the stopwatch to measure the time. Okay, so the meter rule is a resolution of 1 millimeter and a stopwatch usually a resolution of 1 centisecond or 0.01 seconds. He adjusted the water tap to give a constant flow rate. Okay, and the way you do that is by keeping the pressure constant, yeah, to get the same pressure difference across the length. You've got to describe the method to determine an accurate value for the unknown viscosity, okay, of water. Your method should include a suitable graph. So I'm going straight to the graph and I'm saying from the equation we were given, we want to plot a graph of m on the y-axis and t on the x-axis so we can get a straight line graph, because neither m nor t have a power. So m is directly proportional to t, and all the stuff in the middle are all constants. Pi's a constant, rho's a constant. We've made the pressure constant by making sure that it's a constant flow rate. It's due to the fact that it is. We can measure the diameter of the pipe, which obviously isn't going to change during the experiment. 8's a constant. Eta is what we want to determine, which will be a constant because it's for water. So eta, I'm not going to draw a yellow line through it, and L isn't changing during the experiment. It's the distance between the pressure gauges. So if we put on the y-axis the mass and on the x-axis the t, then we will get the gradient y equals mx plus c will be equal to this combination of quantities. And all of them are known apart from eta. So we can make, if we measure the gradient once we got the data, if we measure the steepness of the line between m and t, presuming we're going to get a straight line graph, that is a good, is a valid experiment. We should get a straight line graph if the equation is correct. We can then, from knowing the gradient, the only unknown will be eta, and will allow us to determine it. So that's the theory, that's the hypothesis. That's why I've done it first. We want to know what graph we want to plot, so we know how to do the experiment. Okay, but they want, the key word is accurate value. So you've got to show you know how to create a valid, reliable way of gathering the data. Okay, so the method, you need measurements and you need checks. So checks and measures. So for the internal radius, or internal diameter, I should say, of the pipe, you want to use vernier or digital calipers. Now digital calipers are good because you can zero error them, yeah, and they're easier to use, and they have a resolution which is more accurate, okay? A resolution of 0.01 millimeters, whereas vernier calipers have a resolution of 0.1 millimeters. Then you want to take the average or mean value of the internal diameter, yes, and you want to check the zero error, and other checks will be to repeat at different orientations to make sure that it is circular, to calculate the mean value. So these will get you 2 marks, yeah, and then you want to make sure that the pipe is horizontal. So to ensure the pipe is horizontal, you want to use a spirit level, or if you don't have a spirit level, you can measure the height of the pipe at both ends is equal. If it's equal and the bench is level, then you know that the pipe is horizontal. You then need to collect your data. So these are preliminary checks, 3 marks, and then you want to measure the mass collected at regular intervals of time. So you've got different amounts of mass at different times, so you've got something to plot. You want to keep your digital timer close to your mass balance so you can see both figures, or you can use a data logger, which is actually asked about in the final part of the question. The data logger will take the values for you if you have a data logger that can measure the mass and the time at the same time, so it can sample the data for you. Then you check the pressure difference is constant before taking measurements. Yeah? In other words, that the flow rate has become constant. And you record at least 5 sets of data of mass against time if you're doing the manual method. Minimum would be 5, recommended would be 8. Yes, I always tell my A-level students I'm looking for 8. Then you plot the graph as shown, explained above, and determine the gradient, so you can then calculate eta from all the other values that are known or can be measured in the equation provided. Okay? So that's basically going to get you all the marks. We'll have a look at the mark scheme in a minute. Final part of the question, 10 marker, says the mass balance can be connected to a data logger. Okay? So the data logger records mass shown on the balance. Give 2 reasons why using a data logger would improve this investigation. Well, instead of having 5 points, the data logger can take many more readings in the same time, in a given time. So over the time that you're doing the experiment for, you have a high sampling rate, so you can basically take measurements continuously, almost every 0.1 second, even if you wanted to. It will ensure the mass and the time readings are also taken simultaneously, whereas if you're keeping your eye on both instruments, it's difficult to be 100% certain that you've got the values which are exactly corresponding to each other. And that's how you get the 2 marks for the final 2 for this 10-mark question. Okay? And I've decided I'm going to give this to my students in year 12 on Monday when we get back after the break. Okay, so here's the mark scheme of how you get the units, 2A. Yeah, how you got the units for eta, the viscosity. Part B, measure the internal diameter using the vernier calipers. Repeat the measurements at different orientations or different positions, yes, to calculate the mean. 2 marks. Ensure the pipe is horizontal using a spirit level. They're giving alternatives for doing a check. I think I mentioned these. Wait until the pressure difference is constant before you start taking your measurements. Or keep the stopwatch close to the mass balance is another check. So any of these are checks that will get you an extra mark. And then measure M and corresponding values of T. Get at least 5 sets. It's a minimum required for a graph. And then plot the graph of mass against time. Okay? So there are alternative methods you could use for the graph, it says. But I think my method is probably a good method. Okay? And then a data logger we've gone through for part C. So that allows you to check what they're giving the marks for. High sampling rate. And it ensures that you're measuring mass and time simultaneously. It will probably also do the graph for you, so you could actually get a graph done for you. So it's the automation. They like the use of ICT. So somewhere along the lines, they will ask you about use of ICT in experiments. Okay, I hope you found this useful. I just want to go back to the equation bit and see what they define as R. Yeah, so what we didn't emphasize is here, this is the internal radius, and you are measuring diameter. So you've got to divide it by 2. Yes? And I didn't put that in the method, and neither did the examiner. Okay? Hope this makes sense. So hopefully catch you in the next video. Good luck in your exam on Monday. If I don't see you before that, leave a comment. Don't forget to like and share each video you think will be helpful to other students. Okay? Thanks for watching. Bye.